Hi guys, so what we're going to do now is we are going to run through a bunch of sample problems that all deal with equilibrium constants because I'm not exactly sure what flavor of question that they are going to ask you. As you can see from this document, there are a variety of different ways that they could go about asking you these questions. They could ask you about something while it's already at equilibrium. They could ask you about some dissociation questions, where you're either supposed to calculate the percent dissociation or you're given the percent dissociation. They could ask you about temporary conditions called Q. And then they could ask you to calculate what the equilibrium conditions are. So we've got a dozen or so different types of problems to run through here. I'm going to go through them at a what I consider to be a normal pace. If you run into questions on any of these, by all means, please let me and Mr. Cumberford know so that we can do a better job of explaining some of the intricacies of these. But basically what we're going to do is we're going to walk through each of these guys in turn and see if we can't solve each of them based upon what their particular situation is. So, first of all, we're going to start easy. We're going to start where it says that we are already at equilibrium. All right. If we are already at equilibrium, that makes things infinitely easier because we don't have to figure out a starting condition or anything like that. They're telling us that we are at equilibrium. Now, having said that, I'm going to set you up with what are called ICE tables. And what is an ICE table? An ICE table is ICE, and it stands for Initial, Change, and Equilibrium. So what we're going to do is we're going to take our balanced equation, and over here to the left, I'm going to do I, C, and E. I think we've used these before with stoichiometry and so forth, but it's more along the lines of starting, change, and finish and so forth. But we're going to do initial, change, and equilibrium. Now here's the thing. If they give us initial or they give us change or something like that, that gets challenging. We'll get to those in a second. But the thing that's important for you to know is the equilibrium. Why? Because we have just set up a whole construct on equilibrium. So for example, before I do any of this, I could ask you, what is the equilibrium expression for this equation? So you would say that Kc, why am I choosing Kc? Because it's the brackets, right? If it was the pressures instead, then I would be using Kp, but I'm not. I'm using concentrations, molarities. So because I'm using molarities, I'm going to do Kc. And then we're going to do products over reactants raised to their powers, ignoring solids, liquids, and solvents. So I'm going to do the NO squared, because that's that guy, and there's a 2 in front. And I'm going to divide that by the nitrogen and the oxygen like so. All right? Now, it wants me to calculate Kc. So if this is my x, if this is what I want, then I need to know that number, and that number. And as soon as I know those 3 numbers, I'm in good shape. I'm done. But here's the thing. I need to know those numbers while they are at equilibrium. So these numbers here have to be at equilibrium. Those are the only numbers that work when they are at equilibrium. So if they were to give us initial numbers, those initial numbers that are here could not go in that equation because initial is not necessarily equilibrium. If we were to figure out what the change was, those change numbers could not go in this equation because the change doesn't belong there. The ones that belong there are the equilibrium numbers. These numbers here, these ones here, these are the good ones. Those numbers can go into that equation because they are the ones that are at equilibrium that's there. Now, that's why these problems are so easy, is because they told us, they said these are at equilibrium. So these are already there. So these are the numbers that go for our construct here. So the nitrogen is 2.4 times 10 to the negative fifth. All right, so the nitrogen for equilibrium, I'm just going to move these over a little bit, give myself a little bit more space. They told us that the nitrogen was 2.4 times 10 to the negative fifth at equilibrium. They told us that the oxygen was 3.1 times 10 to the negative third at equilibrium. And they told us that the nitrogen monoxide was 5.2 times 10 to the positive third at equilibrium. Now, you might be saying to yourself, hey, but there's a 2 there. Shouldn't I take this number and multiply it by 2? No. They told us what the number was. Now, if they had given us some initial amount, and if we had to take the change into account there, then yeah, that 2 that was there, we would have to account for when we were dealing with the stoichiometric ratios of everything. But they've told us what the number is. Don't make it complicated. So all we have to do then is take our numbers and plug them into our equation. So apparently our top number is 5.2 times 10 to the third, and I'm going to have to square it because of that's there. And then I'm going to have to divide that by 2.4 times 10 to the negative fifth and 3.1 times 10 to the negative third for those guys, because again, they are at equilibrium. And because they are at equilibrium, I can simply plug them into my equation. So I get out my calculator and I do 5.2 times 10 to the third, and I square it, and then I divide that by 2.4 times 10 to the negative fifth and 3.1 times 10 to the negative third. So assuming I have done my math right, when there's no guarantee that I have, then this is 3.63 times 10 to the 14th, assuming I have done my math right. Okay? So if you are already at equilibrium, all you have to do is plug the numbers in. All right, let's check out number 2 here. This says we are at equilibrium. Fine, done, easy. The only thing that's goofy about this one is that this looks like a fairly complicated K equation. No big deal though. I got an I, got a C, and I got an E. All I got to do is plug my numbers in. So because I am at equilibrium, this is 3.4 times 10 to the negative third. This is 5.1 times 10 to the negative 2. This is 7.2 times 10 to the negative fourth. And, I want to calculate this. So that's going to be X, and they told us what KP is. Easy. So KP then is going to be equal to products raised to their powers, so that's the pressure of HCl to the fourth times the pressure of oxygen to the first, because there's a 1 there. And I'm going to divide that by our reactants over here now. And so our reactants are the pressure of Cl2 squared and the pressure of the steam, the water vapor, squared. All right, they told me what Kp was. They told me Kp was 0.45, so that's easy. So that's 0.45 then, and that's going to be equal to 3.4 times 10 to the negative third raised to the fourth power times, I'm putting this wrong. I apologize. I'm looking at the wrong numbers there. My bad. It's products over reactants. Sorry, I looked at the wrong thing. This is the HCl, that's this. So that's going to be X to the fourth. And then we're going to multiply it by the oxygen, which is this guy here, which is 7.2 times 10 to the negative fourth. And then we're going to divide that by the chlorine, which is this guy here, 3.4 times 10 to the negative third, and that's squared, times the water, which is 5.1 times 10 to the negative 2 squared. So all you have to do now is take this very ugly looking situation that you have, and if you take that very ugly looking situation and figure out what the X value is, then you should have that. Let's see, I think it's this one. Make sure I get my numbers right. Yes, so I think it is supposed to be an X value of 6.6 times 10 to the negative 2 that is here, if I have got my situation correct. I think I do. Yes. All right. So if you solve then for X and take the fourth root of it, you should get a value of 6.6 times 10 to the negative 2. All right. Next, dissociation. All right, dissociation is just a fancy word for change. Okay, and we know about change because we have an ICE table, right? So I'm going to come over here and I'm going to set up an ICE table, I, C, and E. And while I'm at it, I can go ahead and set up Kp, I guess. So the Kp is going to be the pressure of the PCl3 times the pressure of the Cl2 divided by the pressure of the PCl5, because it's products over reactants, like so, raised to their powers, assuming, of course, that it's not a solid, liquid, or solvent. All right, easy. It says that I start with 2 atmospheres of PCl5. So I start with a 2 here. Now, this is no longer at equilibrium. And they've no longer just given you these numbers down here. So we're going to have to earn those guys, right? Now, it says I start with 2 of the PCl5, but it doesn't mention how much I start with either of these guys. And so consequently, I think we can just assume that those are zeros based upon the context clues of what they told us. If there was one of those guys present, it would have had to have given me that number. And since it didn't, we're going to assume that I didn't start with any of those guys. Now, clearly this reaction is not at equilibrium because you can't have zeros and be at equilibrium. So we're going to go over here to the right in some way. Now, what is it going to go by? Well, it says how much it's going to go by. It says that it dissociates by 20%. So that means that this guy here is going to go down by 20%. That has to occur based upon what is stated here. This has to go down by 20%. So what happens is you take 20% of 2, and 20% of 2 should be right at 0.4. So this guy goes down by 0.40, which is 20% of 2. Now, all of your stoichiometry lessons that you learned from before are in play. There's a 1, a 1, and a 1 here. And so if this guy goes down by 0.4, then this guy has to go up by 0.4, and this guy also has to go up by 0.4. So that at equilibrium, this guy is just left with 0 plus 0.4 is 0.4, and this is 2 minus 0.4, and that's going to then be 1.6. That is there. All right? So now we can take all of our equilibrium values that are here, and we can plug them into our equation because, again, our equation works for equilibrium values. So this then is going to be 0.40 times 0.40 divided by 1.6, like so. And 0.40 times 0.4 divided by 1.6 gets you a value of 0.10 as your answer. So if they have told you what the dissociation is, all you have to do is take that into account at the change, because the change means that you have dissociated. All right, let's try another one here. For this guy here, I've got an I, and I got a C, and I got an E, and I want Kp apparently, so fine. So I'm going to do Kp is going to be equal to the pressure of the hydrogen squared, which is this guy, times the pressure of the disulfur that's there to the 1. And then I'm going to divide that by the pressure of the H2S squared, which is there because, again, guys, they're all gases, gas, 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 so they all count. I don't have to ignore anything. And then what did it say? It said that I'm going to start here with 0.25 atmospheres of the H2S. Okay, so fine. So I'm going to go ahead and put 0.25 in there like so. And it doesn't say anything about starting with either of those guys, so I'm going to leave those as zeros. And now what it says is it dissociates by 4%. So I'm going to have to lose 4% of 25. So I get at my calculator and I take 4% of 25, and that means I'm going to lose 0.01 here. Now, be careful. If I lose 0.01 because this equation is going to the right, because you can't be at equilibrium and have zeros that are there. If I lose 0.01, what your brain is going to want to do is just go plus 0.01 and then plus 0.01 over here, and you'd be wrong. Why would you be wrong? Well, take a look at the stoichiometry. It's a 2, a 2, and a 1. So if you want to go here, that's a 2 to 2 ratio. That's fine. That's going to be plus 0.01. But if you go from here to here, there's a 1 in front of there, so that's going to be half as much. So you didn't gain 0.01 of the sulfur compound over here. You only gained 0.005 because all of the stoichiometry lessons that we learned back in the day are still in effect. So 2 to 2 gets us the same amount here and here, but 1 to 2 gets us half as much over here. So you just got to be careful with how you go about doing these things and making sure that you use the correct value that is there, right? So then when you're all said and done, this guy here ends at 0.005, this guy here ends at 0.01, and this guy here ends at the 0.24. You now have all of the numbers that you need in order to take these guys and plug them in to here and here, because again, it is equilibrium that only goes in that equation. And so you end up with then 0.01 squared, 0.005 divided by 0.24 squared. So when you plug all of your numbers in, you should get about 8.68 times 10 to the negative 6th as your answer. All right. What about the next one? What if they ask you to calculate the percent dissociation? Now this is the same exact thing, except what they're going to do is they're going to actually ask you to calculate what the percentages are, rather than giving you those percentages. So all these problems are set up the same way. I got an I, I got a C, and I got an E that's there. Remember that K, let's see, oh, in fact, you don't even need K in this particular equation, but the K is going to be equal to the nitrogen times the hydrogen cubed divided by the ammonia squared. You're not even going to need it, though. Why? Well, let's see. Oh, and by the way, it's going to be Kc because they're dealing with molarity, so fine, there you go. So let's take a look. It says that we are starting here with 0.015 of the ammonia, right? So that's where we're starting. So we're starting with 0.015 of that, and it didn't say anything about those guys, right? Now, here's where it gets goofy. It says, by the time we reach equilibrium, there is 0009 of the hydrogen present. Okay, so by the time we reach equilibrium, which is this guy here, there is 0009 of the hydrogen. So how did the hydrogen go from 0 to 0009? Well, clearly it had to have gone up by 0009. Well, then what happened here and what happened here if that guy went up by 0009? Now, your brain is going to want you to go, well, then that guy went up by 0.0009 and that guy went down by 0.0009 and be done. And you'd be wrong. Why? Because stoichiometry is still in effect. So I've got a 3, a 1, and a 2 that's there. So if I want to go from here to here, that's going to be a third. So this is going to be 0.0003. Or if I want to go from here to here, then that's going to be 2/3. So that's then going to go down by 0.0006. All right. And then when you're done with that guy, you're going to take the 0.015 and you're going to subtract from it the 0.0006, and you're going to end up with 0.0144. All right, so I've got all my numbers filled in, and if I wanted to, I could go ahead and calculate what the K is, and I could if I was so interested. 0003. I could now take all of these numbers here and I could plug them into my equation, but that's not what it's asking for. What it wants is it wants to know what the percent dissociation is. It wants to know this. It wants to know the percent dissociation. Well, remember, the percent is just a part over a total. So percent is always the part over the total times 100%, right? So if I want the percent dissociation, then that's going to be the dissociated part all over the total. Well, which of these numbers is the dissociated part? The dissociated part, remember, is the change. This is how it dissociated. And then the total is going to be where it started. So if it's going to ask you for the percent dissociation, what you're going to do is you're going to take the change and divide it by the initial, and that's going to give you the percent dissociation. So I started with 0.015, and it changed by 0.0006 times 100% means that when I plug all of this in, I end up with a 4% dissociation. So if it's asking you for the percent dissociation, then that is simply going to be the change divided by the initial amount. I started with 0.015. I changed by 0006. Part over the total, that gets you your percent. Let's look at this guy. Same question. A system starts with 3 atmospheres of N2O4 to equilibrium. There's half an atmosphere of NO2 present. What's the percent dissociation? All right, no problem. I got an I, got a C, and I got an E here. If I'm really interested, I'm going to do Kp is equal to the pressure of the nitrogen dioxide squared all over the pressure of the N2O4. It said I started with 3 of this, and it didn't say anything about that guy there. But then it said at equilibrium, there's 0.5 of the NO2 present. Well, equilibrium is down here. So 0.5 of the NO2 is this guy. So we can now fill in the rest of the spots. So if I started at 0 and went up to 0.5, that means this guy must have gone up by 0.5. Now what happened over here? Well, it is a 1-to-2 ratio. So I come backwards at a half, so that's going to be 0.25 to end up with 2.75 down there. But what do I want? I want the percent dissociation. So the percent dissociation is going to be the change divided by the initial times 100%. So that's going to be 0.25 over 3, because that's how much it changed by, that's how much it started with. And so 0.25 divided by 3 times 100% gets me about an 8.3% dissociated. So if they're asking you for the percent dissociation, you're going to do the change over the initial using all of the context clues that they gave you in the particular problem. Number 7. Number 7 is going to ask you about to make a judgment call about which way the reaction should go. So they're not going to tell you that it's at equilibrium, and they're not going to give you obvious non-equilibrium conditions. They're going to give you conditions that it could be at equilibrium. Maybe it is, maybe it isn't. I don't know. So how are we going to do this? Well, let's take a look. We're going to start again with an I, a C, and an E here. And I know that dealing with Kp, so that's going to be the pressure of the COBr2 divided by the pressure of the CO times the pressure of the Br2, products over reactants raised to their powers. Now, please note that what they did is, in this problem, they gave you initial conditions. So all of these are where we're starting at. So the CO, it looks like it's 2.5. And then the Br2 looks like it's 1.4, and this guy here is 5.2. And now they want you to go and figure out what's going on with these guys down here. The question is it's not obvious which way this reaction is supposed to go. Look, if this was 0, then it's obvious that it's going to go to the right-hand side, because you can't be at equilibrium and have a 0, right? What if it was the other way? What if, for instance, that guy was 0? If that guy was 0, then it would be obvious that the reaction has to go back to the left, because, again, you can't have any zeros and be at equilibrium. So what then are we going to do? Well, we don't know if it's at equilibrium until we do a test case. And our test case is Q, and that's called the reaction quotient. And the reaction quotient is literally the same thing as K, except it's a test case. So all we're going to do is we're going to take the equation for K that we developed, and we are going to copy it down here, and we are going to instead slap the label Q on there. All right? So let's check it out. We're going to take these numbers and we're going to plug them in to Q, because again, we can't take those numbers and plug them into K, because remember, the only ones that K work for are at equilibrium, and we don't know if these orange initial numbers are at equilibrium, so I can't do that yet. So instead, what I'm going to do is I'm going to take these initial numbers and I'm going to plug them into Q and see how I did. So I'm going to go ahead and put the 5.2 up here, and then I'm going to put the 2.5 down here, and the 1.4 is down here, and I'm going to calculate Q. So I get out my calculator and I calculate Q, and it turns out that my Q has a value of 1.49. All right, so my initial number is 1.49. Now, what's my equilibrium number? My equilibrium number is 14.5. Does this pink number and this orange number, are they the same? They are not. If they were, then we would be at equilibrium, because if I had plugged these numbers in and I had gotten the number 14.5, well, that means I'm at equilibrium because my value has been achieved. But I'm not at equilibrium. I am too small. So how then am I going to get these numbers here that is too small? So my Q is less than K. How am I going to get my Q to go up? Well, I'm going to have to make these numbers bigger. And how do I make these numbers bigger? Well, I make the numerator bigger and I make the denominator smaller. Well, what does that then imply? If I need to make that number bigger and these numbers smaller, that implies that the reaction is going to go over to the right-hand side. And if it goes over to the right, then that means that I'm going to increase the amount of my products and I'm going to decrease the amount of my reactants, in which case these numbers here will go up and down, and it will consequently make that number bigger. So what you need to know about from this is the following. If Q is equal to K, you are at equilibrium. But if Q is less than K, you are not at equilibrium, not at equilibrium, and the reaction will go to the right in order to make Q bigger until Q equals K. If Q is greater than K, you are again not at equilibrium, and the reaction will go back to the left because your Q value is too big. So the important bit to know is that if Q is less than K, it's going to go to the right, and if Q is greater than K, it's going to go to the left. So what's going to happen here in this particular problem, as it were, because that's what it's asking. Is the system at equilibrium? And if not, which way will it go, left or right? Well, we did all the math, we plugged all the numbers in, and we found out that the Q is too small. My number here is too small. It's got to get bigger to match that number. So consequently, the reaction is going to go towards the products, and you're done. You have solved it. So that was a lot of effort to just tell you that basically, if Q is less than K, it's going to go to the right, and if Q is greater than K, it's going to go to the left-hand side. So let's check out number 8. Number 8 is the same thing. It says, for the reaction below, is it at equilibrium? And if not, which way is it going to go? All right. I've got an I, I got a C, and I got an E. And so it's telling me that this is 0.42. It's telling me that this is 0.67. And it's telling me that this is 0.96. They're giving me the K value. And I know that that's going to be HI squared divided by H2 and I2, which are these numbers here, each raised to their own specific powers. Now, these are initial conditions, so I don't know if those are at equilibrium or not. So instead of plugging them in and assuming it's at K, I am going to copy it down, and I'm going to set it equal to our Q, which is our unknown. So our Q then is going to be 0.96 squared divided by the 0.42 and the 0.67. And when I get out my calculator and plug everything in, I get a Q value of 3.28. And now I double check. My Q is 328. My K is 0.75. So am I at equilibrium? No, I am not, because if I was, that yellow number would be the same as the pink number. And what do I know? The yellow number is too big, and so because the yellow number is too big, those numbers have to get smaller. How does the number get smaller? It gets smaller by making that number smaller and those numbers bigger, which means it's going to go to the left, because if Q is greater than K, it goes to the left-hand side. If Q is less than K, it goes to the right-hand side. So what's going to happen? It's going to go to the left because Q is too big. Number 9. What happens if they give you all of the proper information and instead they want you to figure out what it is at equilibrium? All right, so again, all of these things are set up in the exact same way. I got an I, I got a C, and I got an E. And let's read the context clues of the problem. It says that we're starting with 2 molar of that. So I'm starting with 2 of that. It doesn't say anything about that. And we're doing Kc, so that's fine. So that's going to be C3H7CH3 divided by the C4H10 in the isomerization reaction. And that's all they give me. All right, I can still do this. In all the other problems, they gave me at least one of these numbers down here. Now they're not doing that. Well, let me ask you this. Is this reaction at equilibrium? Well, clearly it's not, because I can't have a 0 and be at equilibrium. So what's going to happen? The reaction is going to proceed. In which way is it going to proceed? It's going to proceed to the right. It's got to go to the right because you can't have a 0 and be at equilibrium. Now, how far is it going to go to the right? Well, in all the other problems, they either gave me one of the numbers or told me what the percent dissociation was. In this one, they haven't. But I know it's got to go to the right. I just don't know how far. Well, that's okay, because I know a number for how far when I don't know. And that number is x. I know this is going to go down by some amount x as it goes to the right, which means this number is going to go up by some amount x. And now this is at equilibrium going to be 2 minus x, and this over here is going to be x. I now have all my equilibrium conditions. Remember, the equilibrium conditions are what can be plugged into this equation up here. So consequently, I'm going to end up with 3 is going to be equal to x divided by 2 minus x, because I can take the products and put them in there and the reactants and put them down there. And I now have one equation and one unknown, so it's just algebra. That's easy. So then this is going to be 3 times 2 minus x is equal to x, or that's going to be 6 minus 3x is equal to x. 6 is equal to 4x. X is equal to 1.5, I think, if I've done my math right here. So my x is equal to 1.5. All right, so let's double check to see if I am correct here, because you can always check to see if you are right. So x is 1.5, so that means that's 1.5, and this is 2 minus 1.5, which would be 0.5. I could then take my equilibrium numbers and plug them into my equation here, and I would get 1.5 over a half, which is 3. And oh look, that works perfectly, because I have the value of 3 that's there. So if they give you your starting conditions and they give you your K, you can use unknown X's to figure out what everything else is. Let's look at a more complex version of this same thing. All right, here we go. I've got an I got a C, and I got an E here. What is it saying? It wants to know what the equilibrium pressures of all the species are if the initial pressures here, so these are the initial pressures, are those guys. So this is 0.25, and this is 0.25, and this is 0 according to that. So I got 0.25 and 0.25 and 0. They told me I have a Kp of 20, so that's fine. So Kp, which is 20, is going to be the pressure of the NO squared divided by the pressure of the N2 and the pressure of the O2. That is there. So that's that and that. Now, they didn't give me any other information besides this. No problem. Why? Because I know that this is not at equilibrium because this over here is a 0, and it can't be. So I know it's got to go to the right. All right. Now, we're going to do this, and we're going to do all of our tricks that we have learned to keep things proper. We know it's going to go to the right, so we know that this has to go down by some amount x. But guys, there's a 1 and 1 and a 2 here. So if this goes down by x, then that also has to go down by x, but this then has to go up by 2x because, again, this is a 1-to-1 ratio, and this is a 2-to-1 ratio. So if these guys each go down by x, then that guy on the right has to go up by 2x. If you'd prefer, you can make this guy go up by x, but then these guys have to go down by half an x, and I don't like fractions. So if you wanted to go down by half an x, down by half an x, and up by x, help yourself. But I don't want to do that. I want to do a minus x and a minus x and a plus 2x. And I'm telling you right now that on the quizzes and the tests, that's the step that you're going to miss because it's so easy to forget. All right, so then what do I have? I have 0.25 minus x and 0.25 minus x, and then I have 2x. So now what do? I take my equilibrium numbers, and I plug them into my equation here. So I now have 20 is equal to 2x quantity squared. And please note that there is a difference between 2x quantity squared and 2x squared. Those are not the same thing. So this is 2x quantity squared because it's the 2x that goes in here. And then down below, this is going to be 0.25 minus x squared because it's 0.25 minus x and 0.25 minus x. Now we reach a conundrum. How do we solve this bad boy here? Well, some of you are really good at those calculators, and if you're able to set this up in those TI calculators and just solve for a real root of this with x, help yourself go nuts. I don't know how to use those calculators, so I'm going to have to do this the old-fashioned way. How do you do this the old-fashioned way? Well, they always leave you an out. If you're doing a quadratic, you're probably doing something wrong. I don't think they're going to give you a quadratic on the AP test. I really don't. So there's a way out of this. What's my way out of this? Well, I can take my 0.25 minus x and my 0.25 minus x, and I can turn that into a squared. Why does that help? Well, because now I have a squared on top and a squared down below, so I can take the square root. So the square root of a square is just that. And if I do that, then I got to take the square root of that, and then that is just that. And then all I have to do is take the square root of 20. And by the time I am done with all of this, what I end up with is I end up with the square root of 20. Let's see, what's that going to be? 20 raised to the 0.5 power is 4.47. So that's going to be 4.47 is going to be equal to 2x over 0.25 minus x. And so now it's just algebra. So 4.47 at 0.25 gets me about 1.12 minus 4.47. X is equal to 2x. So 1.12 is equal to 6.47x, or x is equal to about 0.173 if I have got my numbers right, and there's no guarantee that I did. Looks like I did, yes. Now here's the problem. X is not necessarily your answer, because what does it want? It wants to know the equilibrium pressures of all species. Okay. The equilibrium pressure of none of the species is x. Keep in mind that x is 0.173. So the 173 is x, but that's not this, nor this. So this over here is 2x. So that's going to be the 173 twice. So that then is going to be 346. And this is 0.25 minus the 0.173. So that is 0.077 for both of those. So we can always double check to see if we did okay here, because I could take these numbers and plug them back up into there. And if I do, I should get